This is Premier Dynamics podcast number 31, and today we're talking about how to tell when your CFD has converged. So this is a very important topic because CFD is a very important part of aerodynamics these days, and it's only getting more important. And to tell when your CFD has converged is important because then you can then use your model and look into the aerodynamics and see where you can improve, what you can learn from it, and so on. So we need to talk about how to do that. And that's what this podcast is about. So I have two graphs here to indicate the residuals of a CFD simulation. So let's talk about what these residuals mean first, and then we can talk about how to tell when your CFD is converged, because you use these for that purpose, as well as the forces and the moments and so on. So what are the residuals in a CFD simulation? Well, for both graphs, you can see on the bottom, there's a legend, and it has the three different velocity components. And then there's P, the pressure, omega, and K. So omega and K are two parameters that we solve in CFD. So for these two particular graphs, this is for two different simulations, but they both use the SST K omega turbulence model in the RANS setup. So if you're using RANS, URANS, or DES, then using a turbulence model such as K omega SST or SST omega, whichever one you want to call it, that's going to be applicable. You can use K epsilon, K omega, SST regular, SST gamma theta, SST K omega, and so on. So we have 6 different lines here, all corresponding to these different parameters. And on the face of it, when you just look at both of these graphs, you see these lines and they look somewhat similar. There are these lines that go down over iterations or time. Now, what do these lines actually mean? So when you have your CFD, if you don't know, we actually have a course for CFD. If you want to get better at CFD, check that out. The link is in the description. We go through this and a lot more on how to be better at CFD. But in essence, in a CFD model, whether that's 2D or 3D, you have cells. And these cells, in each of them, you have parameters. So depending on what parameter you're calculating, you calculate it at the center or at the boundary. So these are the 3 different velocity components plus the pressure plus omega plus OK, and a bunch of other things. And the important thing with CFD is when you first run it, you initialize every cell. So you can specify what you want to be in each cell. So you can say that in every cell, the velocity is 0. And then at the inlet, which is a boundary condition, you say, okay, the velocity at the inlet is going to be 20 meters per second. So then that velocity effectively perturbates the system to then make this solution run. If you didn't have any velocity coming in, if it was just 0 meters per second, then the entire flow field that you have, all the cells, would already be correct because they are 0 meters per second as well. You have no flow going in, no flow going out. So it's already converged. But for almost every simulation, there is flow either coming in or going out. So a typical way of initializing a simulation is you say that every cell has a 0 meters per second, and then the pressure and etc. You have those variables for those cells. Then at the first iteration, so iteration 1, you then calculate what each of the values in the cells will be based on the inlet condition and the outlet conditions and the other boundary conditions. And that's obviously not going to be correct because this is now just effectively almost like a guess, because you have an initial condition, which is the inlet conditions, and then now every cell has to adapt to that. But it doesn't happen over just one iteration. You need to iterate through to get all the minor differences out. And that's what happens with every step. So when you go from iteration 10 to iteration 11, you're then recalculating everything in every cell and seeing, okay, based on the boundary conditions, are these cells making sense? Is what's in here making sense in terms of these values? If the answer is yes, then that's good. If it's no, then it means that these cells need to change their values again based on the next best guess. And then you do the iteration. You continually go forward until these guesses in these cells become better and better. Now, these residuals reflect that. These residuals are indicating how much these values in these cells are changing with every iteration. So at iteration 100, let's say on this right graph, you can see that these residuals are hovering between 1 by 10 to the negative, oh, let's say 7 by 10 to the negative 2. 3 by 10 to the negative 3 to, what's that, maybe 8 by 10 to the negative 5. So they are quite small values. But if you have, let's say, 5 by 10 to the negative 2, by 10 to the negative 3, that's still fairly large when you think about every single cell in there. It could be varying quite a lot. So you want to be getting as low as possible. Then you get to a point where it doesn't really converge anymore. You get these little zigzag patterns. We'll talk about them later as well. But this is what residuals mean. It means how are the values in all these cells changing from iteration to iteration. And in this case, we can just call it time on the bottom. Now, these are steady state runs, but the transient runs have the exact same idea behind it. The residuals are indicating how much these values are changing from iteration to iteration. And that's what you want to look out for. The less that they are changing, the more converged your simulation has become. If these lines go upwards, so they are tending above 0, or even worse, like, they can go to 1,000,000 or whatever, then your simulation is becoming unsteady or unstable. It's diverging and it will crash, usually. So that's in a nutshell what these residuals mean. Let's look into how to then determine when your CFD simulation has converged, because that's when you can then say, okay, I can now look at my CFD simulation and start validating it. And then if it does validate properly, we can then use these simulations to look into the flow and make whatever we're looking at better, or learning what we want to from it and do research. If your simulation has not converged yet, then it's not ready to be used in any useful manner yet. So on the left, we have one simulation. You can tell that the time went up to 400. This is 400 iterations because this is a steady state simulation. On the right, this graph only goes up 270 iterations. And that's because this graph on the right converged much quicker than the one on the left. So I didn't have to run as many simulations. So how can we tell that this one on the right converged quicker? Well, first of all, on the one on the left, you can see that these lines, they're pretty good. I mean, at the end of the day, they did always go down. So the residuals are reducing in magnitude, which is always what you want. The only problem is that there were, first of all, it didn't go as quickly. And secondly, there was a bump along the way. So first of all, when you look how long it takes, again, it took 400 iterations compared to 270. So it took much longer to get to a certain value that I specified, which we'll cover a little bit later when I was talking about the zigzags. So we'll cover those bits later. First of all, let's look at this bump and the length of time it took. So on the left, this simulation, it started off and it was pretty crazy. I mean, you get quite a lot of bumps. And what this means is that from iteration to iteration, when you first start, the values in the cells are changing a lot. Not only are the magnitudes great, so that means that the values are changing a lot. It means that from iteration to iteration, it's not getting better. So there were all these zigzags, which is normal when you first start a simulation, when it hasn't really been solved yet. It's just initializing. And that's because all the values in the cells are usually very far off the actual solution. So they're changing dramatically just to get in the ballpark of what they should be before really solving properly. This is part of the solving process, but it's really, you can sort of say that this is really more the initialization process, because the initial initialization was very crude. You just say it's 0 meters per second in every cell. It's not really accurate at all. Whereas this now is really kind of the initialization process. Now you can think of it. Then once you get to a certain point, so in this case, it was around about 60 iterations, you can see that all these lines, they're now starting to behave a little bit more. They're not nearly as jagged, and they're starting to just downward trend the entire time. So most simulations will look like this when you first start off, and then they should hopefully start to downward trend, and quite smoothly. When you see that, that's a good sign. Now, the one on the left, though, when we got to about iteration 193 or something around that, it then spikes up again. So before this point, at iteration 193, the residuals are looking quite good, actually. Like, they are everything except the omega, which has to do with the turbulence modeling on those parameters. All the others are looking very good. They're all very close to 0 in terms of their residuals. They're very small, but the omega is still quite high. So what's going on here? What is the software doing? that this is occurring, because this was done on a commercial software. Most people, especially if you're a beginner or even intermediate, you're not going to be running your own CFD codes. Like good CFD codes that rival commercial software is usually done when you're in a big team in an actual industrial environment and you're all writing code and you use it and it's developed over years. So for example, Lockheed Martin, for example, their CFD code that they use for their fighter jet simulations, that's been developed in-house for decades. And they don't use commercial simulations, at least the people who I talk to there, they say they don't. I don't know if there are pockets there who do, but generally speaking, they don't. And one of the heads of research there who I was talking to not that long ago, he said that they don't use commercial software. They use their own, and they were talking about that they only really use CFD now, actually, not even experiments, because the CFD software has become so good, they can really get away with it. And then they go out and test fly, and then that's the development process there. So in terms of writing your own CFD code, it's a great learning experience, but in terms of actually using it for any useful research, if you're just a one-person team, you're probably not going to be getting a good enough CFD code to rival any commercial software. That's why we use commercial software, which is what's going on here. The problem with commercial software is there's stuff happening that you don't know what's going on. You know, there are relaxation factors, they're solving their equations in certain ways, and that's exactly what's happening here in the left. So as I mentioned, the omega residual is still staying quite high, and then all of a sudden it just drops. So what is going on here? Well, what the CFD software is doing, this commercial software, is to help the solution initialize to begin with. It's putting in artificial parameters, and it's saying keep certain values loose. We don't really need to solve them right now. Let's solve other parameters first, and then we'll start solving the later parameters once these initial parameters have converged a little bit. That way the solution is more stable. If you try to solve everything to begin with, then you can run into instability issues where the values in the cells just don't align, they don't agree, and then you get instability problems. So the residuals go up to infinity or millions or whatever, and then the simulation crashes because the cells are just becoming too unstable with their values. From iteration to iteration, they're changing so greatly just to try to reflect everything else that's going in the system that they just have to adopt very strange values, and then none of it makes sense. The flow physics does not make sense. So these commercial softwares, what they do is they often pick certain parameters. In this case, this one was the omega value. And they said, okay, well, let's not really push this solution. Let's not solve it, this equation. Let's solve everything else first. And we'll keep this one in the mix, but we won't try to influence this solution. Like we won't try to converge it yet. We'll just keep it steady. And then these other values, so the three components of velocity, the pressure, and the K, which is another turbulence parameter, they can converge. Then you get to a certain point where the software goes, okay, well, these values have converged quite a lot now. We're happy with where they're at. So now let's bring in the omega equation and let's try to converge that value now, or that parameter. And that's what's happening around this 200 iteration mark. So now all these other parameters, their equations, which are all influencing each other, including the omega equation, they all influence each other. So now that you have this additional parameter which hasn't been solved or hasn't really been solved properly, that's being thrown into the mix, everything is now being affected by it. So that's why you get this jump up in these other residuals. And now the omega is allowed to solve properly. And then you have this effectively the second leg of the iteration of the solving process. So that's why you get this intermediate jump. So this is the left graph. If you look on the right graph, you don't get that intermediate jump at 200 or even less or higher. There wasn't that jump. All the residuals really tended towards zero quite nicely. The omega wasn't really held at a certain value for too long. It was allowed to converge and solve quite early on. Why is that? Well, the main reason why is because the solution on the right, this was an easier one to solve than the one on the left. What that means is the flow in the right, in the simulation on the right, was more well behaved. At least it agreed with the initialization a little bit easier, that process, than on the left. So the one on the left was a more complex flow, and complex flows are usually much harder to solve because the initialization process greatly estimates. I'm not going to say underestimate or overestimates, because it's really just a misestimation. It's just a wrong estimation of what the values in all the different cells are, because some are very good, some are really bad, some are high, some are too low. So it's not really underrepresentation or overestimation. It's just wrong in general. So this is where these commercial solvers come in, and they say, okay, well, at these iterations, in these from let's say 60 to 185, 190, the solution in this more complex system is still not really very good at all. Like, it's still fluctuating quite a lot. There's just a lot going on. So we can't solve the omega yet until we get the solution to converge just a little bit more, until it's more stable. If we said at iteration 100, let's start solving for omega properly, then that may cause instability in the system, where all the other cells, all the other values in the other cells, they then start going haywire because you have too much complexity in the system, and the flow is just moving in a way that it doesn't mimic physics, like real physics, and then you get just the simulation crashing. So that's why on the left, omega was held at a much higher value for much longer than on the right, because the one on the right, the simulation, was simpler to solve. We only needed to get to iteration 60 before all the different metrics in this commercial solver went, okay, these parameters look good, they're meeting our requirements, so we can now let omega solve. The one on the left, that wasn't the case until much later. So then on the one on the right, the solution converged, and it converged much quicker. That led to that. So now let's talk about when to actually tell when your solution has converged. So we've talked about how CFD works, what these commercial solvers are working, what equations they're using, and how they interact with each other, and how to initialize everything. Now, hopefully things will converge, but how do you tell when it's converged? Well, an overall picture is to say when all these residuals have reached a certain value. So they've all dipped below, let's say, 1 by 10 to the negative 4, or 1 by 10 to the negative 3, or 1 by 10 to the negative 5. What these values mean is that in these cells, between two iterations, the change in whatever parameter you're looking at has only changed by this much, 1 by 10 to the negative 5, or whatever your cutoff point is. Now, what cutoff point should you specify? Generally speaking, the lower the better, but as you can see with both of these simulations, neither of them really get below 1 by 10 to the negative 6. Some of the parameters do, but most of them do not. So what this means is that you can only go really so low before a simulation will never converge. So you need to pick a value and say, okay, well, once it goes below this value, then it's converged. Now, for me, I put 1 by 10 to the negative 6 because I can stop it at any time when I feel comfortable. I can do it on the fly. If you're letting something run automatically overnight and you want it to stop when it's done, then you can put a certain value. I recommend 1 by 10 to the negative 5. That's a decent value. You can go lower if you like, but that may not end up solving. Just be aware of that. Now, you may say, well, okay, these graphs look good, but there are these jagged bits, and what I mentioned before. Why are these jagged bits? That doesn't look great. I mean, it means that the solution is changing and it's quite violent. Well, that is true that there are jagged bits, but you have to look at the scale. So on the left, these residuals, if you look at where the jagged bits are occurring, there are very low values. So yes, the values in these cells from iteration to iteration are different, and they are somewhat discontinuous, but the values, these differences are so small that they don't make much of a difference. I mean, 1 by 10 to the negative 6 is minuscule. So even though there are jagged values, it's not that big a deal because the residuals are so low. If the residuals were at, let's say, 1 by 10 to the negative 2, then yeah, these jagged bits would be very worrying. You wouldn't look at a simulation if there were jagged bits around 1 by 10 to the negative 2 and say, oh yeah, it's converged, because it hasn't. These values are just still way too big. That means that there's 1% change. That's really a lot for a cell for any of these values. But because these values are fluctuating a little bit at 1 by 10 to the negative 6, that value is very little. It's not a big deal. Even by 1 by 10 to the negative 5, that's not a big deal either. Sometimes you might even get fluctuations at 1 by 10 to the negative 3. And let's talk about when that will happen and when that is okay for it to happen. So for a steady state simulation, that's generally not a good thing to happen, especially if it's jagged. But if you have a transient simulation where you have a constant fluctuation, for example, a von Karman street, if you plot some sort of metric and you see that there's this periodicity to it and it fluctuates around 1 by 10 to the negative 3, that's not such a big deal because it's an unsteady simulation and it's a periodic phenomenon. So it actually, the simulation has actually converged. It's just that the solution is not steady. It's transient, so it is going to change from iteration to iteration. And over, let's say, 200 iterations, you go through one entire period of what it is, or of this cycle. So that's not something to worry about. With steady state, if you do have jagged bits at around 1 by 10 to the negative 3, then that would be something that you should be interested in and should really look at and likely try to get rid of. That may mean that you need to run it for more iterations. It may mean that you need to make the cells more refined in certain areas, or look at the boundary layer cells, or look at different values, the parameters that you have in there. But yeah, for steady state simulations, if you have jagged bits around 1 by 10 to the negative 3 or higher, that's pretty bad. For transient cases, so if URANs or DES, LES, whatever, that's not such a big deal. Or it may not be such a big deal. You may need to look into the flow physics and assess that. So those are the residuals, and we use the residuals a lot to determine when a CFD simulation has converged. But not only do we look at the residuals, we look at the forces, or whatever force or moment you're interested in. You can also even look at something else, like, for example, if you want to look at the pressure at a certain point on an object, you're interested in that, you can look at that pressure and see how that's changing with time. If you see that these values, whether that's the force or the moment or the pressure that you're interested in, these overall values, if you see that they're not changing with time and these residuals are also tending towards 0, then you can look at it and say, okay, that looks pretty good. It's converged. Now, how many iterations should you let the simulation go before you can say that the simulation has converged for the force or a moment? So the force or moment may be a straight line. Well, it depends on the history of the simulation, really. I mean, for example, let's say you have a simulation, unsteady simulation, that's running for 5 seconds. And for the first 4.9 seconds of that simulation, there's all these jagged bits, and it's just going crazy, chaotic. And then the last 0.1 seconds, so from 4.9 to 5 seconds, it's flat. Would you say that that's converged? Probably not, because for the first 4.9 seconds of that simulation, the forces were going all over the place, and now it's only converged for the last 0.1 seconds. That's maybe not the case. Maybe it hasn't converged yet. So you should let it run for another second or two to see if it plateaus out and whether it behaves itself, whether it goes back up and shoots up and goes crazy. At the end of the day, you need to just look at what's happened in the past in this simulation, in the residuals, and look at how they behaved. If they behaved very well before that and the force is just slowly plateauing out, then you can let it run for another half a second or whatever and go, okay, the simulation has converged. If it hasn't plateaued out, it's just been very chaotic, and then it plateaus out for only 1/10 of a second, then you need to look into that and think, okay, well, it may not have converged yet, because this may just be a local effect, and then it will just go out of whack again later on. So you need to look into that. So I just want to pause here and say, make sure you check everything to Geoprinarics. We've been talking about CFD in this podcast. We do CFD courses, so you can take them and become a better CFDer, which is where the future is going to be. But also experiments are good, because we need to validate our CFD as well, and they're not going to go anywhere either. So we also do courses for experiments. We also do courses for theory, so you can understand all of this. So check out our courses, links in the description. We also do instrumentation for experiments. So again, experiments, your CFD validation is only as good as your experiments. So you want to have very accurate experiments. We make instruments to help that happen. We have instruments to measure the density of air in your experiment, so you can actually tell what the density is instead of just assuming it and having these errors. We make traversers, we make PIV systems. Check them out, links in the description, and check out the International Aerodynamics Conference we put on every year. It's a conference for every aerodynamicist to get together and talk about aerodynamics and meet and greet each other and network. So check those links out in the description. So let's come back to how to tell when your CFD simulation has converged. Let's recap everything that we've been talking about. So these residuals, they tell you how the values in each of these cells are behaving with each iteration. The higher the residual, the greater the fluctuation between two neighboring iterations in a cell, in a given cell. So you want to get these residuals as low as possible. That means that these values in these cells are reaching a solution. They're staying constant, they're staying steady. And this is what these residuals reflect. So you want to get them to be as low as possible. Along the way, you may get certain bumps. If you get a lot of bumps, then you want to really make sure that you run your simulation even longer, or even go back and refine your cells in certain points. Look at the thermokinetic energy where that's high in your cells and refine those regions to get the thermokinetic energy down. Again, if you don't understand what that means, check out one of our courses. We explain it in that. But yeah, then you can run one simulation again and see if it converges a little bit better. You can look at the time stepping. You can drop that, or you can look at the iterations for the time stepping to help your simulation converge, get those residuals down. You can also look at the force and the moments and pressures or whatever other parameter you're interested in and see how that is converging with time, whether it's plateauing out, whether it's reaching a certain point and stays constant around that. If that occurs, then you can be, and your residuals are quite low, then you can be quite confident that your simulation has converged, and you can use that simulation to do your research or do the design and development. That's it for this podcast. Make sure to like and subscribe. Check out other podcasts. Check out everything we do at Aerodynamics. Check out our courses. Check out our conference, and check out our instrumentation that we do. And I'll see you in the next podcast. Peace out.